Hello. Unfortunately, in the second video for Chapter 6, the very end, like the last 20 or 30 seconds, got cut off while I was working out the problem. So in this video, I'm going to go ahead and redo this problem, and I'll even do another example tutorial, so that way you can have another example of how to work these problems. So in this problem, we're going to determine the de Broglie wavelength of matter. In this example here, we're looking at an egg that's rolling with a constant velocity of 0.1 meters per second, and we're assuming now that friction is negligible here. The very first issue that we have to deal with is the fact that we have mass, and the mass of the egg is in grams. However, Planck's constant has joules in it, and a joule is equal to a kilogram times meters squared over seconds squared. Okay, so because of this, we need to convert our grams into kilograms. Alright, so when we do that, we have 100 grams. We have 100 grams is equal to times 1 kilogram divided by 1,000 grams. And in doing this, we cancel out the grams and we're left with 0.1 kilograms. Now we want to solve for lambda, which is the wavelength, and we're going to be using Planck's constant, which is 6.63 times 10 to the minus 34 joules per second. Okay, one thing that I always suggest that you do is make sure your units cancel. Okay, so if you notice, we have a seconds, and one of the seconds canceled there. Then we have a second here, and the second on the bottom. We have a kilogram on the top and a kilogram on the bottom, a meter on the bottom, and 2 meters on the top. So we're left with a meter, which makes sense, because wavelength is going to be a length. And so the final answer is 6.63 times 10 to the minus 32 meters. It's ridiculously small. Okay, which makes sense. That's the reason why we don't see the wave nature of the egg with our eyes. So let's work a more difficult problem using the de Broglie wavelength. So here we want to use the de Broglie wavelength relationship to determine the wavelength of an 85 kilogram person skiing at 50 kilometers per hour. And so the equation is wavelength is equal to h over mass times velocity. We have to remember a couple of things. Remember, h is equal to 6.63 times 10 to the minus 34 joules seconds, which is the same thing as saying 6.63 times 10 to the minus 34 kilograms times meters squared divided by seconds squared, because that's what a joule is, times a second. The hard part of this is, since joules has meters and seconds in it, we need to convert kilometers an hour to meters per second. So let's do that first. We want to take 50 kilometers per hour. We know that 1 hour is equal to 60 minutes. Likewise, we know that 1 minute has how many seconds in it? 60 seconds. So now we got seconds on the bottom, which is good. Now we got to cancel out the kilometers. So if you notice back here, the kilometers, that's on the top. So that means that we now need to put 1 kilometer on the bottom, and 1 kilometer is equal to 1,000 meters. So let's check to see if the units cancel out to make sense. We have a kilometers on the bottom and a kilometers on the top. Hours on the bottom, hours on the top, minutes on the bottom, minutes on the top. And so we are left only with meters per second, which is what we're wanting. So now you multiply by everything on the top, you divide by everything on the bottom. And if I've done this correctly on my calculator, I get 13.89 meters per second. So that is our V. Now we just, to find the de Broglie wavelength, we just have to put lambda and we have to plug in chug. We have H, which we wrote up above already, 6.63 times 10 to the minus 34. And I don't want to skip any steps, so I'm going to go ahead and put kilograms, meters squared, over seconds squared, times seconds, because that's what joule seconds are. Divide that by the mass, which mass was 85 kilograms, that's given to us in the problem, times when the velocity that we've already figured up, which is 13.89 meters per second. Now before we go any further, let's see if our units cancel. We have a second. Oops, I said second squared, I forgot to write it in there. We have a second, and it cancels with the first second. That second and that second cancel. The kilogram and the kilogram cancels, and one of the meters canceled out. So the only thing that we're left with here is a meter, which is what we're looking for, since we're looking for a wavelength. So we multiply by everything on the top, you divide by everything on the bottom, and you're going to get some ridiculously small number. It's 5.6 times 10 to the minus 37 meters. Hopefully this has helped you learn how to manipulate and use these equations in order to determine the Broglie wavelengths. I'll see you in class.